Good evening, everyone. Welcome to today's session on week 2 Applied Accelerated Artificial Intelligence course. So, first, let's start with the previous year assignment, then we will brief the today's week 2 session. First question uh, which one is the container orchestration tool for clustering and scheduling Docker containers? The Docker Hub is a cloud-based registry for sharing Docker images, and the Docker Cloud is a service for deploying and managing Docker containers in the cloud, and whereas the Docker container is a standard unit of software that uh, packages code and its dependencies. So the right answer is the Docker Swarm. It is a container orchestration tool for clustering and scheduling Docker containers. Next question. State whether the following statement is true or false. Kubernetes can balance and distribute network traffic to maintain the stability of a deployment when container traffic is high. So the correct answer is true. Kubernetes can indeed balance and distribute network traffic across containers to maintain the stability and the uh, available deployment when the traffic is high. And this is done through the services like the Kubernetes services, which can perform the load balancing. Next question. Which of the following provides registry capabilities for public and private content? This we have already seen. Docker Hub. Docker Hub provides the registry capabilities for public and private content, allowing the users to store and share Docker images. Whereas the Docker Cloud, it is a service for managing and deploying Docker containers across across the cloud providers, but it is not primarily a registry. It's like more about the Docker Cloud is more about like orchestration and deployment. Next, Docker container. This is not a service or a platform. It's actually a lightweight standalone. executable package that includes application and dependencies. And containers are what is run and not where you store or manage the images. And Docker Swarm, we have already seen, this is a container or orchestration tool that is used to manage clusters of Docker engine and schedule containers. So it does not provide any registry capabilities. It's focused on running and storing the container. The next question. During the app deployment with the command kubectl create deployment, we provide the answer is both deployment name and the app location, app image location. So the command is like kubectl create deployment, the deployment name and the app image location. So we need to provide the deployment name, name that we are giving for the deployment, and the app image location, uh, the Docker image that we want to deploy. So say example, uh, create deployment, say the name, my app image. So this is the deployment name and this is the image location. Going to the next question. Choose the correct statements. So the correct statements are VM virtualizes the computer system and the container virtualizes the operating system only. And the why this is not true, containers are not more secure. Uh, this statement is not true because containers share the host OS kernel, so they have smaller isolation boundary compared to the virtual machines. So with respect to security, it is not true. Going to the next question. Kubernetes services in K8s is created using the which of the command? So CTL expose is the correct answer. This is used to create a Kubernetes service to expose a deployment or a container or like a pod or any other resource so that it can be accessed inside or outside the cluster. Whereas this one, we use deploy command. This is not a valid command. Whereas if we have this run, is used to create a new pod or a deployment, but not specifically for a service. And execute exec is used to execute commands inside a running container. So this is a new pod or deployment. And this command it is used to execute a command inside a running container. This one is used to create a Kubernetes services. Correct answer. Going to the next question. Which one of the following is an open source, fault tolerant, and highly scalable cluster management and job scheduling system for Linux cluster of the thousands of nodes? That is SLUR. This stands for Simple Linux Utility for Resource Management. And this is an open source, fault tolerant, and highly scalable cluster management and job scheduling system for Linux with thousands of nodes. This Kubernetes, it's a container orchestration system mainly for managing containers or containerized applications. And this is a framework for distributed storage and processing of big data using MapReduce. And Dockers are a platform for deployment or using the containers.
Could you please repeat the function added once?
So, next question. Which of the following are the key functions of Slurm? So, first option, allocates exclusive and or non-exclusive access to resources to user for some duration of time. Yes, it is the operation of Slurm. Next is provides a framework for starting and executing and monitoring work on the set of allocated nodes. This is also true. Uh, Performing real-time virus scanning and malware protection for computer nodes. This is not correct. Arbitrates contention for resources by managing a queue of pending works. This is also true. So 1, 2, and 4 option. Security is not a key function. Next question. Which of the following statement best describes Minikube? So Minikube is a plugin that enhances the security of the container. So security plugin is not uh, what to say description for a Minikube. Minikube is a graphical user interface tool. It's not a GUI tool also, and it is a command line tool. It's not specifically managing containers, images. Okay, so this is not specifically managing this. So the right answer, Minikube is a lightweight Kubernetes implementation that creates a virtual machine on your local machine and deploys a simple cluster containing only one node. This is the gut. Next question. Dockers are used because they provide standardization and productivity. This is true. Continuous integration and rapid deployment. This is also true. Compatibility and maintainability. This is also true. So answer is 1, 2, and so now let's brief the week 2 session. Just summary. So this is a generic ML workflow for a machine learning, deep learning algorithms. So first is to get the source and prepare the data, and then is to design the model. So next we need to train and evaluate model on a common shared platform. So what is a common shared platform? So let's say DGX. So there is a cluster which is commonly available to all the teams, different teams. So we have a respective model or an application, but running in a centralized facility. So it's like a big cluster and it is shared among multiple users, say like DGX. So we should know how to use a shared hardware. So once we train and evaluate the model using a common hardware, we need to test the model and then deploy the model. So in the generic machine learning workflow, on an average, 40% of the business is set to take more than a month to put an ML model into production. In this scenario, like how we are going to optimize in such a way that we put in little amount of effort just to put any ML model which we design into production. So there are a lot of software dependencies to handle because we will see like there will be different teams working on different types of framework, different types of operating system, the version, and all have to run on the same hardware. So we need to access the same hardware but have different framework, different approaches to solve. And like we need to deploy a version control problem. So these are the three problems basically which we encounter when we are working on a shared, common shared hardware. So next, the dependency problem. So this is a shared hardware. It can be a cluster, say like a DGX server, or it can be a system which consists of multiple GPUs. And on that, we want to run an operating system. That operating system will have to run certain projects. So let us say that we have two projects and one team is trying to work on TensorFlow with a Python version 3.8 and trying to access a GPU and working on a CUDA toolkit 10. The other team, the project 2, is working on a PyTorch using the Python 3.7 CUDA toolkit 11 version. So there is a particular team requires a particular set of requirement version, and all these are supposed to run on the same operating system and then on the same hardware. So this is the dependency problem. So now this is a kind of a dependency problem. We cannot have more than one version of a software because it will have clashes about the drivers from the different toolkits. So if say a person installs everything on one operating system, then how we will have different, say if this is installed, say let's say one person wants CUDA toolkit 11 and the next person, the other project team requires 10. In this case, there is actually a dependency problem. So this means ultimately we can run only one project. And as we are bound to install everything on the same operating system. So this problem of version control, say this three project teams is reviewed by a review team. So there is a team A, B, and C. All the three teams say they are submitting the code for the testing. These projects are from different teams, so they will have different requirements. So how are we going to set up these environment? Because it is running on a system, uh, one hardware. So and also if it is running in one particular system, it should be running effectively in another system given the same condition, the same framework, the same dependencies. Now say if we set the system for team A, uh, review team B and team C could have done something else with different framework, some different versions. So in this case, it's very hard to set up the system for review right from the scratch, and processing it will take a lot of time. So what are the possible solutions because of this different versions? So the basically two possible solutions. One is the virtual machine and the other one is the Docker and containers. So what is virtual machine? You have we have the hardware and the host operating system. Mhm. Hardware, the host operating system, the hypervisor, and then the project one, which is running in a guest OS Ubuntu with a Python 3.8 and its CUDA toolkit 10, and then another virtual machine which is running in some other operating system, Linux operating system with version 3.8 and CUDA toolkit 11. So these are isolated virtual machines. So project 1 could also work on this, project 2 could also work on this. What is the issue in this? It's a computational overhead. Because guest OS in both of that virtual machines will be bulky or heavy, so it takes a lot of memory. Version control and virtual machine solution. So to ease and what are the possible solutions, effective possible solution will be use Docker skill. Now in this case, let us say team A review have a separate project image. Team B also has a separate project image. So the images have the full OS and will be larger, so that the only thing which is Sorry, just give me time. So the solution here is again doctors. Say a team A is having a separate image file, a team B is having a separate image file. So the review team, like say, only thing is these images, if they have like full OS, then it will be larger in size. So that will be a disadvantage. So, so the Docker solution. So images with full size will be larger. So the solution we set is Dockers. So in the Dockers, we have a hardware, host operating system, and a Docker engine. So the project one container, and we have a project two container, and its own framework, and this has its own framework, and it's totally isolated. So now in the review aspect, these images will have the projects, and they will be easy to share and manage the versions, as we got a separate project image. Now Docker accessing the GPU. Dockers are actually like gives a lightweight solution compared to the virtual machines. And in the case, like we want to access the GPU, say a Docker image is running a PyTorch project through this operating system. The hardware, which has the access to the GPU, and is achieved through the port forwarding. So this is done like here, the system from where we are trying to run this Docker on this hardware on, and then we are going to the project through the web browser, and like we can work on the Jupyter notebook, and the overall idea is like mm, working with the Dockers. So now uh, we have this client. Uh, this is a Docker host, and host will have a lot of containers, and we will be having a lot of images, and this is controlled by a Docker daemon. And then we have a registry from where the Dockers could be pulled. So like two registries were shown in the NPTEL lecture. One is the registry from the Docker Hub, and the another one registry from the NVIDIA NGC cloud. So we can pull those containers, and the idea is like how is the setup with which the like we can work on with the Docker. So this Docker container lifecycle, the Docker container lifecycle, we create a Docker container where like we can run it pause it, stop it, or stop it. So, or delete it. At the various stages, we can do all this operation on those Docker containers. So this is the brief idea. Like once a Docker container is created, we can run, pause, stop, or delete on that Docker container. So uh, in the NPTEL slide, Docker demonstration was demonstrated with a command called like docker run hello world. So this few Docker commands were demonstrated with. This is a command. If the Docker is not available in the cache, so it will be like showing unable to find that image locally, and then it will be like pulling it from the library, and which is the latest library from the Docker Hub. So just skipping this demonstration part. Next, we will see the scheduling and resource management, introduction to the schedulers and orchestration tool. So this is like a CPU kind of architecture and a GPU architecture. This is like a CPU representation, and this one a GPU representation. So CPU nowadays like at least at most 80 cores, whereas GPU are for high throughput. So they are like high throughput based architectures, and they have thousands of cores. And like latest GPU have more than even 5,000 cores. So when we have more number of cores on a particular processor, like this is one core, this is one core. So more number of cores on a particular processor means that we can launch so many parallel operations on that particular processor. So on GPU we can launch say thousands of cores, so thousands of parallel operations, and this all basically represents accelerating computing or throughput based computing. So accelerated computing or throughput based computing. So all the artificial intelligence or high performance computing applications, which includes like molecular dynamics or computational fluid dynamics or as simple as event sorting, can be converted into a parallel operations. And all these parallel operations can run on a architecture like GPU. So we can train the model much faster as compared to in the traditional architecture. And now let's just this. So now let's see what is this virtualization and containers. Virtual machines is like as a technology was the base of the cloud computing, and with cloud computing uh, was to have like a centralized location, and we can optimally use the resources and schedule them across multiple users. So say a particular system which was like very heavy and one user could not use the whole system. So we can actually create multiple virtual machines on the same system so that we can efficiently utilize the whole server or the whole machine more efficiently. So it is actually a resource optimization problem. And from the technology, like it's like efficient, we are trying to solve the problem like efficient utilization of the resources. So we are seeing that the host operating system, then followed by there is an entity called as hypervisor, which makes sure which will make that like, so say this virtual machine is not aware of this another virtual machine which exists. So it feels like this is utilizing the whole server, and this is done using the hypervisor. And there are like we have seen different types of hypervisor and different types of virtual machines. So next, containers. The fundamental like difference between the virtual machine and a container is that the server infrastructure, we have the host operating system, and uh, here we do not have any entity called as hypervisor which was acting like an OS over an operating system. And so what we have here is a container. So the container will act like a bundle where all the dependencies are bundled into one entity, and it is running on a container runtime. So here the container, and the reason why the containers became famous is that containers do not go through the hypervisor. There are high chances that almost provide, it's like it provides the same performance when it is like this is going to be run on a non-hypervisor, non-container environment. So it's like we are directly running the application, and if we get the performance latency, it is will be almost similar when we run using the container runtime. So it's like a very thin layer, and it helps in bundling all of the dependencies and running it on the server infrastructure. So we can achieve a lot of things like which are there in the virtual machine. But container has its own problems, like we cannot basically like create a separation of this separation, where there is like no guarantee that one container might not be able to access the resources of the other container and things like this. But suppose say we implement a neural network and we install all the dependencies, we create a container and host it on one of the repository. So we will be able to run that container on the, say, on my machine. I can run it on another machine, where so I can run it on the cloud. I can run it on any other particular uh, machine, say, without having to install or reinstall any other things. The question is, in which case could the latency be more on whether the virtual machine or the container? In the container, the layer used is very thin layer. So in general, virtual machine should have more latency compared to the container, because of very thin layer. That's why we said this one. If there is performance without this container layer, and the performance adding this container layer is almost similar. So that's challenges accelerating big and small. So this AI advances demand exponentially higher compute. AI is advancing at an exponential rate. Mm, say, like advancing not just in the accuracy, like accuracy is increasing or the error is going down, but also the models are becoming more and more complex, and we need to increase the compute power to train the networks. So in 2012, the network which won the ImageNet challenge from AlexNet, and then later we can see ResNet. There is a 300x gain just in this 3 years from the previous model, and so the amount of compute need increased by 3000x. Sorry, this is like almost 3000x. So the problem, this is the first problem. The second problem is the other side of the AI world problem. So the number of sensors is also increasing. So the amount of data which is being pumped in by the sensor is huge. So all the data needs to be analyzed by the network or the model, ML model. So there are like billions of searches happening on Google, and all these different search engines, there are so many sensors which are like there are so many interactions which is happening, the amount of videos getting uploaded, the photos getting tagged. Now this is a different problem altogether compared to this first one. So here AI powered interaction needs varying amount of compute. So the first problem is about training the network, and the network is itself a huge. And the second problem is basically we have a trained network, but we need to scale out to make sure that we are able to like get the data from multiple sensors. So it's like a scale up problem. This is like a scale up problem, and this is like a scale out problem, because we need to cater to so many users, and that is the problem which the enterprise of or the AI like deploying an AI is trying to solve. So it's not like just creating and improving the accuracy for a particular data set, but it is much more than and like that. So next, HPC evolution. So this is a single core CPU. Like in the earlier days, the performance in the mega flops range, which consists of a single core CPU and attached to a memory. Next, when the computation increased, we have more than one core. So like one core is not enough to solve the compute requirement. So we came to the multi-core era, where we have like a processor with multiple cores and a shared memory. So nowadays a processor consists of like almost 80 cores. So 80 machines, core machines, all sharing the same RAM. So 80 or 160 one threads running in parallel, accessing the shared memory. So this achieves some mega from the mega flop to gigaflops. Next came the distributed system. So now we distribute the work across in this overall network to different machines, and then accumulate the results into a particular uh, base. So this is called as distributed computing. And in this distributed computing network, which is not in the same, because it uh, uses doesn't use the same Ethernet cable, like 10 giga bits per second. It is a very high throughput, low latency network. Example like InfiniBand, which goes up to 400 Gbps, and all like it is like much higher speed and low latency compared to the traditional Ethernet cable. So next is like in this core, along with the GPU, we are having a CPU. We are having a GPU. So in the same cluster, along with the CPU inside the node, we also have a GPU. So the advantage is that more computation on a single node. So next, what is a cluster? So the definition of a cluster is a computer cluster is a set of computer nodes that work together, and it may be viewed as a single system if required, like trying to solve the first problem, which is to run large models across all of them, scheduling and control. So we consider the whole cluster as a one big single system and run the job across so many nodes. So, or can we solve the other problem also, that getting from like scale out? So here the basically we are required to work on both control and schedule of the scheduled of by a software. So AI use cases. So the first uh, one, suppose an example, uh, you are in a college there and there are so many students, so many users in, so we have so many nodes on the premises, like so there are so many users and all of them have to access the many nodes, which is, or it may be like where we want to access only one system and there are multiple users, which means that we want to access a system and there are many users and many users are like requiring the resources, they that might be having an overlap between the jobs with each other. So our third type is more of this is requiring the same resource, or a third type is like a cloud busting hybrid approach where we are trying to run things on our own machine, but once we exceed a particular threshold, The cloud bursting. Sorry, system is hanging. Yes. So here we were like trying to run it on our own machine, and once the workload increases, or like so we put or bust that particular part to the cloud vendor, say a Google cloud or an Amazon cloud. So there is another scenario which is edge or IoT. Edge computing part, which plays very important role in terms of say deployment, where we are going to deploy our machines. So like where are we like going to train, and then finally we are going to deploy it on an embedded device, which may be like scattered across for performing various inference tasks. So the next so we see here the necessity of AI application. um, we have different requirements. Like I make sure that my job is transparent. Like every job gets a fair like resources. So the resources, next comes the challenges with the resource utilization. So here the fundamental like the problem to solve here is the resource utilization problem. So the users needs to coordinate and among themselves, and there might be places where resources might even go unused if not properly coordinated. So it is not a scalable model having this dedicated nodes. It is not a scalable model and it is very difficult to maintain. So we cannot just keep on adding machines and expect everyone to like schedule their jobs. While in the cluster environment, so here the coordination is required. In the clustered environment, where like we have a particular software, so here the less coordination is required, and we have a set of software stack installed. So because of which there is less user coordination. Say we need how much of number of cores, based on that it will be allotted. So it is highly scalable, and if it's a standardized for maintenance. Next, AI cluster component. So we have said that this InfiniBand, so the network are not the traditional 10 giga networks, but we have like InfiniBand networks which uh, gives up to 100 Gbps or 200 Gbps also. And so this is part of the overall cluster component, so we can communicate faster not just the computation is faster, but also the communication across the nodes. So we have a network which is connecting the different user like nodes. We have say a node where we are going to run all the jobs, which means like we have a cluster node or a compute node where the actual computation will be happening. So like in a environment like GPU, CPU, GPU node, here say we have some 10 or say X number of them, and all these nodes are connected to each other via high speed Ethernet, such as InfiniBand. And we spread our work across those nodes, and then we can accumulate the resources using this high speed network. So that like every node like does not have its own storage, but have the storage which is like a network uh, file storage, which means that all the nodes can see this same storage. So if you want to access one node, the other node or uh, the home directory or all of the files are actually mounted on, and they are there in this particular storage, which is a common for all the nodes. So especially in AI, we require a high speed storage because AI, like we are seeing gigabytes of images, like there is so much of data, gigabytes of data. So we need very high speed storage, and not just the compute should be faster, but also the communication should be faster. Data and the storage should also be very fast. So what is scheduling? So we need to access the hardware, and it's not like by default the it is given to one particular user, and that is done. So it is the hardware. It is like done by using a software or a framework, which is called scheduling, and say like so. If say this job requires this many nodes, so the here the idea is like X number of compute resources which are known to the scheduler or is a part of the configuration, which means like how many nodes I have. These nodes have how many CPU cores, how much memory, and how much GPU. All those are known to the scheduler, which is going to manage this scheduling task. So the user say comes to the cluster and submits a submits a job, and like there will be multiple users. So every user submits a job, and which each job contains uh, like how many nodes it needs. So say the slum is one the manager, and it sees what to do, what is your the requirement, and based on the free nodes, it provides the uh, say this job asks for 3 nodes, then it allocates the 3 nodes if there is an availability. So, this is a popular scheduler known as slur. which is a simple Linux utility for resource management. It started with a simple resource manager. It has like 500,000 lines of C code, and it's easy to use. So we can run it on our PC also if but generally it is used in a cluster environment. Yes. The glue for parallel computer to execute the jobs parallelly. So the base slum components. So from the architecture point of view, the slum consists of two main components. The first one is called the controller, and the second one is called the compute node. So if you consider in the user login node, there are two types of nodes: the login node and the compute node. So in the login node, in is the one where we have the controller, and in the login node, it is running a daemon. The daemon is a slum control. This slum controller, like slum sctld. So it runs as a daemon, and basically user is going to ask this which is running to basically allocate certain compute resources. So the compute node is going to run another daemon which is slur md. This slur md is basically the daemon which is going to listen to the manager, and basically the slur md will tell the manager that okay, this is free and how many resources are free and like all these things. So there are some optional components also in this. So it's like a client server or a manager and a slave like model where we are going to have a master, and the master is going to give the job to the slave who are going to basically do it and then give the results back to the master. So job submission. So what can we ask from this manager? So say like we need 1 GB, 2 GB, 4 GB, or we need one computer, two computer, how much memory, how much compute nodes, how many compute nodes. So these things we can ask when submitting a job. So we can ask for number of parallel tasks that we are going to run. Say like if we are going to say that we have a task which utilizes this like 4 cores. So we need within a core one node, and within a node 4 cores. So if the cluster had like 16 cores, it will take away those 4 cores and give it to the user, and the other cores will be used for the other users. So we can ask the number of GPUs that we want for in a particular node. We can define the quality of service, which we'll see in the other sessions. following weeks? I hope so. So we can define other parameters, number of tasks that we need per node, and like we can share those resources with some other user also, and the different things that we can provide when submitting a job. Slum common commands. Uh, so the command like s info will tell all the resources which are there on the cluster, so that we can know like how many resources are available, how many are are available, how many are present, how many are used, and who is using it, and all those things. Similarly, we can check the jobs that have been submitted and that have been completed, that uh, so these are some of the commands. Okay. Container orchestration for clusters. The next topic is Kubernetes. Uh, so the overall thing is called orchestration, which means that we are trying to orchestrate all of those features and making sure like following all those principles and optimally utilizing the resources. One of the orchestration layer is called Kubernetes. We can think of Kubernetes as an operating system for the cluster. So now for a cluster, you can think of Kubernetes, which is doing many of the things that operating system does. But all the resources which are across the nodes and not just on a particular machine. Like now for a cluster, it is Kubernetes is the operating system, and it can do all the things that an operating system does, but for all the resources which are across the nodes and not just a particular machine. So it's across the nodes, whereas operating system is just like for a particular machine. So we can think of it as a higher level operating system which takes into consideration all the resources of the complete cluster. So this difference, what is the difference between orchestration and job scheduling? So traditionally the cluster has been like very heavily tied down to high performance applications like say computational fluid dynamics, while orchestration is very much relevant to the artificial intelligence applications, and it is like especially adopted by the enterprise segment with large across all of like basically for AI, and this is for high performance HPC, high performance for the AI workload, and this is for the high HPC. Think we will go to the next. So the need for Kubernetes. So so the containers are good way to bundle the application. So the container deployment needs to be done on a centralized hardware, and there could be people using lot of such containers. So there has to be basically a mechanism by which these containers need to be managed. So whether a person is managing it or there is automated Kubernetes software which does it, or there are certain other scheduling and orchestration softwares. So somebody needs to manage it. So if we see that the way containers are good way to bundle the applications, because like we have all the libraries, application, the dependency, everything in this one container, like in the containers. The containers like belong to a team and say A, and this container belongs to say team B, which might be running a different application with different libraries, binaries, and but it is going to basically run on the same hardware. So the container by that mechanism are a very good way to bundle the applications. So now we need to manage the containers that run this application and ensure that there is no downtime. Downtime. So the concept is that we have got a very high performance cluster. It has to work 24 by 7, 365 days, and it need not have any downtime. So downtime is like some service to the. So so how do we manage such like say without any downtime? So for example, suppose a container by say any probability goes down, so we should be able to ensure that similar type of container or that container is again restarted. So if this downtime is handled by some system, instead of a person monitoring it, it could be like uh, useful if this particular, like instead of a person ensuring that there is no downtime, we want like monitoring done based on the some software. So even if the nodes goes down or something happens, we have some sort of redundancy into the system. So this is the Kubernetes is a framework to run distributed system uh, resiliently. So here, what we are trying to come up with is with a system where we are trying to ensure that the type of a distributed system which has got lot of compute elements, say GPU, CPU, and memory, everything, which is going to run resiliently. Even though like we have a redundant nodes or redundant compute units, so this redundancy helps to run the system without any faults. So and it takes care of the scaling and failure of our application, and it will provide some say some deployment pattern. So this is very high level view of what a Kubernetes does. So the first thing, so let's see what are the like very specific things which what is the importance of Kubernetes. The first thing is the service discovery and load balancing. So it does is service discovery and load balancing. So the service discovery is something like Kubernetes is in a position, right, to actually understand or using either a DNS or its own, uh, say it exposes a container using its own DNS, or it has own IP address, and then it can rediscover all the services available on the DNS name or the IP address. And if the traffic to the container, in the sense the container could be using certain services or data, or it has to send data, or if it that is the case, like if the traffic to the container is high, Kubernetes is going to help balance the load. So it will help in balancing load balancing, and it will help in actually distributing the network traffic so that the deployment is stable. Now, like basically this means that from the network point of view, we are trying to load balance the traffic. So say we have got say you have got let us say 5 nodes, and say everyone wants one node because everybody knows wants one node. So everybody gives that one node, and what efficiently happens in is node 2, 3, 4 are all free. In that case, load balancing, like say so there are 5 nodes, but everyone is asking for the node 1, but this nodes 2, 3, and 4 are all free. So here that load balancing or the workload is more on this node. Instead of just trying to run it on the node 1, we can distribute and balance it. So the first thing of service discovery and load balancing is actually done by the Kubernetes. The next thing is the storage orchestration. So the storage orchestration means when we like you are trying to work with Kubernetes, say for example, deep learning algorithms. When we have a container, that container will have all these things, but we will have to have a storage from where we are pumping the data to the particular model. So when we are working with a huge amount of data, because we are working with DL application, deep learning application, and each of these deep learning application require a lot of data for training. So if the data is not sufficient, we will be performing data augmentation to create a lot of data, like at our end for the to use in the deep learning application. In this scenario, the Kubernetes also allows you to automatically mount, link the storage of whatever choice we have. Say you will have local storage, storage from the cloud, or storage from the laptop. So these type of systems that for the storage has become important feature of Kubernetes. So this helps the orchestrate storage. Next is automated rollouts and rollbacks. So these are very important thing ensuring consistency across the caches, across all the nodes. All of these needs to be taken care, and Kubernetes does automated rollout and rollback. So let's consider, like we describe a specific desired state for our container using Kubernetes, and so say there is a desired state, and we have deployed a container. We will see the deployment, like you could have seen the deployment in the demo session. So the deployed container that actually uh, describes the Kubernetes. Kubernetes can change the actual state to a desired state in some fixed amount of time, or maybe some control mechanism. Using some methodology, it can actually help to attain a desired state. So we can automate also the Kubernetes to create a new container for our deployment. Uh, Next, another thing is automatic bin packing. Or let's say that using the Kubernetes on a cluster of nodes, we know that this cluster node is going to actually run the containerized task, and we will tell now the Kubernetes that how much CPU or and the memory each container requires. Like we can allocate that also. Like this particular container, this particular user will require this many CPUs, and this is the memory which could be required by this container. So the Kubernetes is going to fit or allocate the container to those nodes which are actually going to make the best use of the resources. So we will ensure that resources are used very efficiently. The next is self-healing. Self-healing basically means that like the Kubernetes installation or the setup is going to restart the container that actually could have failed. We can also replace the container, or we can kill the container based on the certain criteria. So the those containers, those are what are those containers are called as user defined health check thing. once the container which is running, and if we are providing some services through those container to various clients or users. So if we define certain health check and ensure that if they are not satisfied, they are not going to advertise them to the other clients until they are ready to serve. So indirectly it is ensuring the quality of the service also. And the next is the secret and configuration management. So this helps to store and manage sensitive informations, password authentication tokens, SSH keys. So these are all part of configuration management, and this is all basically like ensuring these have to ensure security and secrecy for this matter. And we can actually deploy and update secrets and secured information and application configuration technically without rebuilding again the image containers and without like exposing this information in the stack configuration. So this is why Kubernetes is very good for the application which we are trying to run on the cluster, which we are going to use it in the which we are going to run on the clusters. Okay. What is the difference between Docker Hub and Docker Registry? So Docker Hub is a like a public Docker registry service, whereas the Docker register is the underlying open source technology that stores and serves the Docker images. Say like a storage Docker registry is like a storage and distribution system for Docker images. And it can be public, which is like Docker Hub, or private, which is self-hosted in the in a private or say our own organization. Is it clear? So Docker registry is a storage and distribution system for Docker images, which can be public. If it is public, then it is a Docker Hub. And there can be private repositories also. So I hope I have answered your question. Just a second. I hope by DB you mean database. So Docker registry is not a, database. It is a service. Yes, I think so. Both the Docker registry and Docker Hub are services. But once I will confirm and then we can discuss in the next week class. Actually, from my understanding, Docker registry consists of public, which is a Docker Hub, and a private. So Docker Hub is a public Docker registry. So the components of Kubernetes. We So we assume that, say we have a cluster and uh, we want to deploy Kubernetes onto it. Say node A, node B, and node C. And then we have the compute nodes. We have got the login nodes. So there are various types of nodes available. So when we deploy in a cluster, what effectively happens is we have to actually manage all these nodes. So in this diagram, we are seeing that there are 3 nodes. Now these nodes are supposed to be in the cluster, and then this node actually, if we see, are linked to the cloud through the control plane. So the cloud is a service cloud. Like somebody is providing us the service and we have the application program interface API from the service provider so that we can use this particular cluster. So what effectively happens at the user point is that we can access through the cloud this particular Kubernetes cluster in such a way that we are in a like position to get the facilities which are running on this node. Kubernetes cluster will consist of set of worker machines. The terminology we use is worker node or worker machine. That machine is going to run containerized application, and each cluster in which like we say a cluster, it should have at least one worker node. So assuming that this is one is a master node, and in the like we have different terminologies here, the control plane. So okay, how to accelerate real training using GPUs. So I think we have framework for that, like the CNN. What is the difference here using Python packages versus custom CUDA implementation? For the existing uh, say convolution operation, we have a very optimized code which can perform better in GPU. Or if something is newer layer which we are trying already those packages are highly optimized. Maybe if we can further optimize and the custom CUDA implementation will be better. This is needs actually and the link we provide them in the next section. So the various components in terms I will take those versions. And then let me brief with this question. How to accelerate DL training using GPU? So as I said, using the framework like CUDA, CUDNN. So and efficiently using them, we can accelerate the DL application. So any other doubts? Okay, one thing when we are saying Python package and a custom CUDA implementation. Custom CUDA implementation is like say it's little complex and say to write and debug. And also we have to see the whether it is flexibility like between the platform, the framework, and as I already said that the CUDA packages like the Python packages are already highly optimized. So if some new layer we want to try, maybe the custom CUDA implementation give better performance, or we can maybe like are able to further optimize the existing one, then it's going to have a better performance. Any other questions? So if you want to uh, optimize some operation which libraries are not available in the Python package, then this will give a better performance. Custom CUDA implementation. Okay, so if no doubts, then we can end today's session.
Ma'am, ma'am,
Yes.
ma'am, good evening, ma'am.
Yes. Good evening.
Ma'am, that is, I only posted the question.
Ah,
I want to ask one more point, ma'am.
yes.
Actually, I wanted to work like GEM optimization, GEMM, General
General
Matrix
matrix
Multiplication.
multiplication. Yes.
But already some packages were there in Python. Directly we can use the GEM. But my doubt is, ma'am, we have plenty of multi-GPU cluster environment. Everything is there.
Okay.
In which way I can add a novelty, ma'am? Apart from Python packages, which are implementation side, suppose I want to add some novelty in accelerating DL applications in terms of training or inference, whatever. Is it using GEM, say for example, is it, can I say it is a novelty part? Like that I'm having the doubt.
Maybe you can try novelty through data flow, the way you process the data, the way you process the neurons. Like either you take the first layer, complete it, or take some weights based on the weight axis. This maybe you fetch some weights, you complete the complete operation by the weights, then you fetch another set of weights. So something related to the data flow. or yes, that only at this point I am able to think. Can you think of something with respect to the data flow?
Yes, ma'am. Yes, ma'am.
I think there are many papers which focus on this way of like instead of like taking one layer, completing the implementation, or taking a particular set of weight, completing the complete computation required by the weights, then going for the next set of the weights.